to use Etabs compared to a TAM project. I hope you already received the drawings and the design criteria to use in the TAM project. There are six groups for the TAM project, and I will explain the design criteria and brief of the project. Then I will go to the Etabs module. Okay, this is the project number 1. In this building, we have the center core, and this building is an office building, and periphery columns. And for each project, I gave you, for all projects, I gave you 3 types of buildings. But group 1, for example, group 1 and group 4, same floor plan, but the design parameters will be different. So only 3 buildings will be there. So this is for group 1. So in this TAM project, you have to use ACI 31808. And also the loading, for the design loading, you have to use the minimum design loads for buildings and other structures, ASCE 705. And material properties, I simplify them. We will use only 2 types of concrete strength. For vertical members, columns and shear walls, we will use 55.2 megapascal, and for beams and slabs, we will use 34.5 megapascal. But in real projects, we will have different types of concrete strengths depending on the story level. For example, in columns and shear walls, in the lower levels, we will use the higher concrete strength, and then we will reduce gradually to the upper level. But here I use only 1 type of concrete strength for concrete and shear walls. For reinforcing steel, we will use the yield strength of steel 414 megapascal. And these are the design loads. For gravity loads, we will consider 3 types of loading. One is the dead load, self-weight of the structural components, and second one is the superimposed dead load. Superimposed dead load is for the floor finishing and also partition walls and other equipments which are connected to the ceilings or floors of the building. So for superimposed dead load, we will consider 3 kilopascal. For dead load, when we model in Etabs, it will be automatically calculated by the program. And live load, we will consider 1.92 kilopascal for all floors. This one, we make it very simplified. In the real project, there will be more type of live loads. At the corridors, we will have a larger live load, like 4.8 kilopascal. But here, I make it simplified. And the second one is the wind load. For wind load, in this group 1, we will use 120 miles per hour and exposure type C. And importance factor, these are normal buildings, not the important buildings, so we will use importance factor of 1. I will explain how to import those loadings in the Etabs later. The third one is the seismic load. For seismic loading, you have to conduct equivalent static analysis as well as the response spectrum analysis using IBC 2006 response spectrum. In old days, we used UBC 97 code for the seismic loading with the seismic zone factors. But these days we use ASC's 7 seismic loading, which is based on the spectral acceleration, based on the which are obtained from the probabilistic seismic hazard assessment. So those spectral accelerations you can get from the code. But in ASCE document, those values are for the US cities or US maps. But if you use local building code, some countries, they have their own maps. So you can get those information from the building codes. There are 2 spectral and acceleration values you need to know to import for the seismic parameters. The first one is the spectral acceleration of a short period, which has 0.2 second structures. So in the buildings, 0.2 second is approximately 2-story buildings. That value for this project is 0.8 g. G is the acceleration due to gravity. If you use meter per second squared, it will be 9.81. And the second one is for the 1 second natural period spectral acceleration. That one is 0.3 g. Spectral acceleration means it is not the ground acceleration, it is the acceleration of the structure. Do not confuse with the ground acceleration. In that area, if the ground shaking coming for that earthquake intensity, so the structure of 2 second natural period will shake with 0.8 g. Okay, so that ground motion is has a return period of 2,475 year return period, which has the 2% of probability of exceedance in 50 years. It means that if we design for that level of earthquake, there is a chance, there is a 2% chance of exceedance when the earthquake comes. So there is a chance, 2% chance where the earthquakes which are stronger than the design earthquake. That one, long transition period, just use 8 seconds. And site class. Site class is based on the soil. If your project is located in soft soil, site class will be D or E. But if your project is located on the good soil, hard soil, or rock, it will be C, and if it is rock, it will be in B. And importance factor, we will use 1. And for the number of story for this project, it will be 35 story, and typical story height is 3.1 meter. And for the foundation, you have to use fixed supports for the columns and pin supports for the shear walls. In this project, you do not have any basement levels, only typical floor. But in real projects, there will be basements and the podium levels. So the drawing that I showed you is the architectural drawing. You have to develop the structural system and then conduct the structural analysis for gravity loads, wind loads, and seismic loads. Then you have to present the mode shapes and time periods of the building. So if your natural periods of the buildings are not within the acceptable range, you have to adjust your structural system. And also you have to present the model participating mass ratio and story drift, displacement, and the wind and earthquakes. Then you have to present the base shear of the building in terms of weight of the percentage of weight of the building. So when you calculate the weight of the building, you have to consider dead load, 100% dead load, 100% superimposed dead load, and 25% live load. And also you have to design some members, 2 main columns, 2 main beams, and also 1 shear wall. I will show you how to conduct the design in Etabs for those members. So this building is for group 2. This building is a residential building. It has the shear walls, and also you can add the moment frames. So this will be the shear wall layout you can use directly from the architectural drawing. And one thing, when you model the building, you can simplify the location of the columns and shear walls. For example, in this grid, center of the column is not exactly on the grid. But when you create the model, you can put the column on the grid. Okay. Okay, this building is for group 3. This is also a residential building, and mainly resisted by the center core. So in this building also you can model the core and also add the columns around the periphery of the building. And when you model the core, you need to connect the shear walls with the link beams. And if your natural period of the building is not in the acceptable range, you may need to add some beams connecting to the between core and the columns. And when you check the natural periods and mold shapes of the building, for the natural periods, for example, if your building is, let's say, 40-story building, the natural period of the cross-section model should be around 4 seconds. 50-story building, it will be around 5 seconds. But when you want to calculate, when you want to check in more details, I suggest you to use the height in feet. For example, if your building has 200 feet, it should be 2 seconds. Sometimes in real projects, the story height is not 3.3 or 3.1 meters. Sometimes it may have 4 meter, 4.5 meter. In that case, number of story, determining the natural period based on number of story may not be accurate. And for the mold shapes I prefer to get the translation in the first mode. Translation either X or Y direction. But torsion in the first mode, it is not preferable in seismic design. For group 4, the building plan is same as group 1, but the design parameters of the group 4 is different from group 1. I changed the design criteria of group 4, especially in the wind loading, seismic parameters, and number of story. Okay. So I will continue how to model in Etabs. When you create the new model in Etabs, first you have to do is select the units. The default unit is US customary. We do not use, we are not going to use US units, we will use SI units. So we will change the unit from US customary to metric SI. And then you have to define the grid system based on your architectural plan. You select the grid only option here and then create grid only. Then you can adjust the grid layouts based on the architectural dimensions. So you can go to edit and edit stories and grid system, and then you can modify the grid system here. And also you can change the number of stories. You can edit the number of story here as well, modify and show story data, and you can add more story and change the height as well. I will explain you how to define the material properties and also define the beam sections, column sections, and shear wall sections. So important thing that you need to define is the material properties. Go to define and define materials. Then in the default material you will get the 4000 psi, but if it is now we are going to use two types of material for the concrete strength. So you have to define the new materials. So add new material, and then you can select the material type concrete, and then you can, there are some default concrete properties. If it is matching, you can use, but if not matching, you have to select that one, and then you can modify it. For example, if you want to use 8000 psi concrete, you have to change it to 8000 psi. For example, I will show you here. This one you can give any name, 8000 psi, and then important thing is the elastic modulus of the material. If you make mistake here, your analysis results will be wrong. That one you have to take care. Okay. So this E value you need to calculate by yourself. This 155.2 each, which is equivalent to 8000 psi concrete. So I will show you how to define. Okay. In calculation of E, when you use SI unit, for the concrete strength less than or equal to 6000 psi, you can use the equation of equation of 4700 Okay, this equation is for concrete strength of less than or equal to 6000 psi. So you can use this equation for the beam and slab material properties. This one you have to import in megapascal unit. If you use PSI unit, this one will be 57,000. But if the concrete strength is higher than 6000 psi, you have to use other equation. Okay, these are the equations for F prime C less than or equal to 6000 psi. This one for PSI. 4700 is for SI unit. And if it is more than 8,000 psi for columns and shear walls, you have to use this equation for the calculation of elastic modulus. Okay, so this one you have to calculate and fill it here. And also important thing is you have to check the weight and mass of the material carefully. But normally if you select from the default properties, they are correct. And then you have to change the design data here. So if you use 8,000 psi, you have to change this one to 55 megapascal for the concrete strength. This information will be used in the design process. Same thing you have to define for the rebar properties. But here the rebar property is already defined. So you can directly use this rebar property. Here this one is already 414 megapascal. After you define those material properties, you can define your frame sections and wall and slab sections. Okay. Go to define section properties, and then these are the default ones, but you can define the new properties, concrete rectangular, and then use, okay, for example, this one is for beam. So you can give the name, let's say you are using 500 millimeter with 800 millimeter depth. And then you can select the property that you define. And then you have to fill the dimension of your beam. You have to take care that the first information is the depth. Normally we call the beam with width and depth 500, 800, so 800 is depth. But here when you fill, you have to fill that depth first, not the width. So depth will be 800 and width will be 500. Okay. Then you have to go to the modify and show rebar. For the beam design, you have to select the design type M3 only. Sorry. Here. Okay, here we have to select the design type from for the beam design. This member will be designed as beam, and then you have to provide the cover to be considered in the design and reinforcing property that you have to use, and then you can click OK. But here there are top bars and bottom bars in this form, but for the normal linear analysis and design, you do not need to fill this information. The required reinforcement will be calculated by the program automatically. This information is needed when you conduct the nonlinear analysis. to calculate the moment capacity of the beam. For example, you already know the longitudinal reinforcement top and bottom, so you have to provide here. And the program will calculate the moment capacity of the beam and provide the moment and provide in the moment hinge. But this one is not needed here. Another one is the property modifiers. When we conduct the strength level design for, especially for the seismic loading, we have to consider the crack sections, because under the earthquake, the beam, the structural members will be cracked and damaged. So we have to consider cracking effect of the members. As I showed you before, when we import the seismic design parameter, we import for 2,475 year earthquake, which we call it maximum considered earthquake. The strongest earthquake that can come for that site. So in the code, when we import those parameters and the code reduce that maximum considered earthquake to design level earthquake by 2/3. So we design the building 2/3 of that strongest earthquake that can happen in 2,500, let's say 2,500 year. Okay. So, and also in earthquake design, we allow damage in the building, because if we design the building to remain elastic under earthquake, the design cost will be very high. The construction cost will be very high, except for the very important buildings. If the structure is very important and we cannot allow any cracking or damage, so in that case we will design the building to remain elastic. But for the normal residential building, we allow yielding of the members, and for that one we reduce the design forces further by the R factor, which we called overstrength factor. If we provide the good ductility in the structural system, we reduce the design forces with a larger R factor. For example, R factor may be 7 for the special moment resisting frames. So we divide the design forces by that R factor. So we designed the building to be yielded in the strong earthquake. So in that case, we have to reduce the stiffness modifiers of the structural members. Normally in the code-based design, we reduce the stiffness modifiers to 0.35 for the beams. We just need to reduce here we just need to reduce M3 only, because in beam M3 is the major axis of the member. M3 means moment about 3 axis. Okay, we have to reduce to 35%. Others you can keep as 1. Okay, this is for the input for the beam properties. And another property I will define for columns. Just use rectangular sections, and it will be column. I prefer you to start put the initial C for the column sections and initial B for the beam sections. So for example, column size is, let's say width is 800 and depth is 1200. And then you can select, here I haven't defined 8000 psi. After you define, you can select. And depth is 1200, and also width will be 800. Then you have to select the rebar. Here for the columns, you have to design for M2 and M3, axial and flexure interaction. Then in column, there are two options here. One is reinforcement to be designed, and another one is reinforcement to be checked. In this building, for the new project, we have to design the column. So we have to select the second option. The program will calculate the reinforcement, vertical reinforcement, and report you. But sometimes we already know the reinforcement and we want to check that design is adequate or safe. In that case, we have to choose design reinforcement to be checked. So in that case, the program will report you the demand to capacity ratio. If demand to capacity ratio is less than 1, design is safe. If DC ratio is more than 1, you have the column capacity is not adequate. And you in the column design, you have to provide the reinforcement data. The default is 3 and 5. The number of longitudinal bars in 3 directions means the bars which are parallel to 3 axes, local 3 axes, and 2 direction means the bars parallel to local 2 axes. Here, when you import the bars, I suggest you to, the initial bar spacing, I suggest you to make a 300 millimeter spacing for the bars. For example, if we have the 1200 millimeter depth, so just divide by 300, so there will be 300 is quite big, so 150 millimeter spacing of the bar. So 1200 divided by 150 and provide the bars in 2 direction, and 800 divided by 150, so you will have the bars in the 3 direction. This is just for initial trial. And for the reinforcing size, just start with 25 millimeter tire. So here you have to select the rebar tire of 25 millimeter. Okay, both corner bars and the side bars, they are same diameter. And confinement bars, you have to use the 12 millimeter tire and provide the spacing of 100 millimeter. This is not important for the design process. The program will calculate the required shear reinforcement based on the area per length. Then you can click OK. Then for the columns, you have to specify the stiffness modifiers like beams. But in columns, you have to consider both directions, M2 and M3. So in that case, but for the columns, we considered 0.7 for the stiffness modifier for the moment. 0.7 for both direction. Others you can use as 1. So in your building, you can you have to define maybe for the columns 5 to 10 sections, and beams maybe 5 to 10 sections. Okay, but for the columns, I would like you to reduce the column size after 10-story interval. I don't want you to use one column size from ground level to the roof. Okay. For example, now we defined 800 into 1,200 millimeter, but after level from foundation to level 10, then level 10 to level 20, you can reduce 100 millimeter in depth. You do not need to reduce in width, but from 8,000, 1,800, 1,200 to 800, 1,100, something like that. Okay, or maybe you can reduce 200 millimeter as well. 800 to 1,000. Yes. Sorry, 800, 1,200 to 800, 1,000. You can reduce to the upper floors. For the beams, if you want to use the same size in the upper floors, it would be okay. But columns, I prefer you to reduce the sizing. And next one will be the slab sections. For the slab sections, there is a default property, just use modify show, and then you can, for example, if you want to 200 millimeter thick slab, just give the name as 200 and fill here 200. Okay, and but if you want to use 250, just change it 250 here. And for the modeling type of the shells, I suggest to use the shell thin in the slab. For the shell thick, we will consider in the thick members like the mat foundation, let's say 3 meter thick, 4 meter thick, but for the slab, just use shell thin. Do not use membrane. And another thing is, in slab, you do not need to specify the reinforcement information for the design. And you have to specify the stiffness modifiers in slab as well. In the slab stiffness modifier, for that one I would like you to reduce to 0.25 or M11, M22, M12. M11, M22, M12 are the out of plane stiffness of the wall, flexure stiffness, sorry, out of plane flexure stiffness of the slab. So this one will be 0.25. This one also 0.25, and this one also 0.25. Okay. Then click OK. And another thing is for the shear walls, you have to define. You can add new properties, and then you can give the name. If, for example, wall with 800 millimeter thick, and then you have to select the material properties and the thickness, define the thickness, and also shear walls will be sharp thin, and find the property modifiers. In that one, for the shear walls, we have to consider the crack section for the in-plane flexure stiffness. In that case, you have to use F22. F22 is you use 0.7. Okay. I will share these stiffness modifiers to you later. Okay, and will send the stiffness modifier summary. And also you have to reduce the out of plane bending to 0.25. Then click OK. When you define the shear walls for your dam project, do not start with 200 millimeter thick or 300 millimeter thick shear wall, because this is tall building. 200, 300 will not be enough. So you better to start with 600, 700. Sometimes you may need around 1000 millimeter. Okay. Then I will continue for the massos. For seismic analysis, we need to define the massos. Normally we consider 100% of dead load, superimposed dead load, and 25% of live load. So here there is a default mass definition. In this one, we normally use specified from load patterns, the third option. Okay, so sorry, I have to define the load patterns. Let me start the load patterns. Okay, first we will define the load patterns. Default one is the dead load and live load. In dead load, you will see the self-weight multiplier of 1. So it means that the self-weight of the members will be automatically calculated by the program and considered as dead load. You need to use self-weight multiplier 1 in only one time. You do not need to use in self-weight multiplier in live load as well. Okay, if you consider like this, your self-weight of the building will be considered 2 times. So this one will be only 1 time. Then you have to define the superimposed dead load. then add new load, so superimpose that load is defined, and also you have to define the earthquake load and wind load. I will show you wind load first. So for wind load, you have to define x direction wind load and y direction wind load. So let's say x direction wind load. Then you have to select the wind load type. Then you have to select the code that you want to consider. For example, if you want to consider the SCE 710, you can consider as a new load, modified lateral load, and then there are, okay, after you click modified lateral load, you have to fill the wind input parameters. How to apply the wind load. For the tall building projects, we normally applied from the exposure from the extent of the diaphragms. If you want to apply exposure from the shell and frame objects, you have to draw the cladding of the building and apply the pressure coefficients on that shell elements. This is quite tedious, so we will apply on the extent of the diaphragms. Then you have to specify the wind speed. Wind speed should be input in miles per hour. So in the design criteria, if I give you 120 miles per hour, you have to use 120 here, and exposure type you can select B or C or D. Exposure type B is in the downtown, but D is in the open near the shoreline. Okay, and then topographic factor you can use as 1, and gas factor please use 1. Okay, in the meantime. But these gas factors needs to be calculated according to the code, in which it depends on the natural period of the building. If your building is flexible, gas factor will become larger, more than 1, 1.1, 1.2, but in the meantime, use 1, okay? And directionality factor, use 0.85 default value. And for the exposure height, use from base to the top of the building. But if you have the basement levels in your project, you have to neglect those basement level, because we do not need to apply wind load in the basement level. You have to start from the ground to roof. And then for the wind exposure parameters for the direction, just consider 1 in the meantime with eccentricity 0. Okay, there are 4 cases, but we will consider only the first case for your in the TEM project. Other cases are if the program will apply the wind load with the eccentricity, but we are not going to consider in the meantime. So this is for the wind pressure coefficient, wind input, and also this one, the pressure coefficients. You can let the program to calculate, as well as you can specify by your own. But here you can let the program to calculate. This wind pressure coefficient is depending on the plan shape of the building. Let me show you in the code. Okay, these are the CP coefficients from the code. For windward wall, it is always 0.8. Windward wall means, okay, this is the building in plan. So if the wind coming in this direction, we always consider breadth of the building as is perpendicular to the wind direction, and length of the building is parallel to the wind direction. So this one will be windward and this one will be leeward. So windward is always 0.8. But leeward coefficient CP will vary depending on this breadth and length ratio. So if the breadth and length ratio is L by B ratio is, for example, 0 to 1, it will be 0.5 minus 0.5. If it is L by B ratio is 2, it will be minus 0.3, and if it is more than 4, it will be minus 0.2. It means that if the building is long, for example, this building is very long, in that case, the leeward coefficient will become smaller. But you have to take care, if the wind is coming in this y direction, this one will become B and this one will become L. Okay, you have to take care of that one. But if you let the program to calculate automatically, you do not need to check that one, so the program will check automatically. But in this building, we consider the typical floor only, but in the real projects, the floor plan may vary in the lower floors because of the podium. So in that case, better to import manually. And one thing I forgot here is wind direction. I forgot here. The fault here is 0 degree is in X direction. So wind X is 0 degree, here X direction. And if you want to define another wind, so value Y and add new load and modify lateral load, and you have to change here wind direction to 90 degree. So this will be the Y direction wind, and you have to change these parameters. Next one will be earthquake cases. Here we will define the earthquake loading for the equivalent static analysis. And you have to select to seismic, and then select ASCE 7, which, let me check which code. Okay, ASCE 705. So wind also you have to select ASCE 705, but the parameters are okay. If you use gas factor 1 and others, they are okay. Okay, this is for earthquake. So earthquake X, we will consider only X direction without eccentricity, and also you have to import the program calculated natural period. Uh, this natural period is not based on the model analysis natural period, so you have to check based on the code. First, let me explain this portion. Okay, here we have to import the spectral acceleration values. This one you can get SS value from the design criteria. For example, this SS value is 0.65 and S1 is 0.32. So you have to put 0.65 and 0.32. Then long transition period according to the design criteria, and site class you have to select either B or C or D, but B is the rock soil, so there is no amplification in the site class. If you use the soft soil, for example T, you can see this becomes 1.28 and 1.76. These parameters are increased. It means that our seismic demand is increased due to the soil amplification effect. Then so in that case, the program will multiply that 0.65 with 1.28, and then final design will be 2/3 of that value. So the final value will be 2/3 into FA into that SS and S1. Okay, that one will be the final design value. But the program automatically calculate, so you need to import SS, S1 and site class. Then you have to specify the response modification factor. In UBC we call it overstrength factor, that R value, based on your structural system that you select. Here in the structural, for the structural system, you have to see according to check in the code. There is a table 12.2-1 for the seismic force resisting systems. There are different types of systems with R values to be used in the seismic design. I will give you those building codes later, so you can check the R values from those tables. For example, if you want to use the bearing wall system, special reinforced concrete shear wall without the moment frame, for example, especially in the core wall building that I gave you. So in that case, you can use that system and parameter column without the beams. So in that case, you have to use r equal to 5. So you have to specify r value of 5. And system overstrength factor you do not need in the calculation. So just change r value. And for the story range, you can consider from base to roof. But in the real projects, if you have the basement levels, we do not consider the basement in the seismic mass because the basement cannot shake, cannot be accelerated because due to the restraining effect of the surrounding soil. Then the last one is the CD value. CD value, it depends on the structural system. You can select from the code. Here table 12.8-2. So if you use the moment resisting frame, steel moment resisting frame, it will be 0.028, concrete moment resisting frame only 0.016, but in your projects they are shear walls, so it will go to the all other structural system. Okay, so you have to use the last one, which is 0.02 and 0.75. So you have to use the last one for your projects because you have the shear walls. Then okay. Same thing you have to define for the earthquake in Y. And then modify lateral load, then you have to check only Y direction earthquake. Then input the parameters same as before. So these are the load cases that you have to define for linear static analysis. After that, I will define the mass source. So mass source will be defined as a specified load patterns. So we consider 100% of that dead load here, superimposed dead load here, and live load will be only 25%, 0.25. Okay. But some people they consider only the storage loading for the storage live load in the mass source. But here we consider all live load, 25% of all live load as a mass source. And we will check include lateral mass only. We will not consider the vertical mass, and we will lamp all the lateral mass at story levels. But if you have the transfer system, there is a transfer girder and column is resting on the girder, you better to consider the vertical mass as well. Then okay. Then I will show you how to define the response spectrum analysis. So first, for the response spectrum, you have to define the response spectrum functions. So you have to define the response spectrum function and select the code, ASCE 705. And then add new function, and we will write ASCE. You have to fill the SS and S1 parameter here again, and also site class, and then you have to, and also you have to specify the damping ratio. Normally we use 5% damping in the response spectrum for design earthquake. Then you click OK. In response spectrum function, you need to define only one time. No need to define for X and Y. We will use the same function in analysis case. Then you have to go to the load cases. Here in load cases, whatever the load patterns that you define, it is already defined as linear static. And then you have, for the response spectrum, you have to add another case and select the response spectrum, and this one I will give the name RSX, and then I have to add the function to be analyzed. Okay, default is function name is default uniform, so I will select the ASCE spectrum and scale factor. Scale factor here is 9806. It is in millimeter per second squared. Okay, if your unit is in meter per second squared, you have to use 9181. Now we do not need to change. And also you have to select the direction. This one is X direction, U1, default U1 is X direction, so just use U1. And modal combination, you just use CQC, and directional combination, use SRSS. And modal damping, just use 5% of damping, of critical damping. Then same thing you have to define for RSY. Add copy of case, and then you can define RSY. Then you have to change this one to U2, and other parameters are same. Okay. Here we use 9806. So it means that we are applying the seismic loading of design earthquake, full seismic loading without reduction by R factor. Okay, so from response spectrum analysis, you will get the elastic base year, the elastic design base year of the building. But from the equivalent static analysis that I defined, we already import R factor. So the elastic base year will be divided by R factor. So when you compare the equivalent static base year and response spectrum base year from the program, equivalent static base year will be quite smaller than the response spectrum base year, because here in this import we do not have any R factor in the response spectrum case. So for the design, in design we have to, if we use the response spectrum cases, we have to scale down the response spectrum results to equivalent static base year. Because if we design with these results, our building will remain elastic under design earthquake. There will be no yielding, and the design forces will be very high, and column sizes, wall sizes will be large. So we have to scale down to the equivalent static analysis. Generally, those design earthquake, which is 2/3 of the MCE earthquake, it is approximately the return period. It has approximately the return period of 475 year, but it is not always true. But we assume that it is about 475 year, and we design for that earthquake. But for the wind, Now we are using ASCE 705 loading. The wind speed that we specified based on ASCE 705 is 50-year return period. Okay, but when we design and using the load combinations, we have to multiply with the load factors in the load combination for the wind load. In that case, we multiply the load factor of 1.6 in the load combination in front of the wind load to convert that 50-year return period wind loading to 700-year return period. So we are designing 700-year period wind loading for ultimate strength design. For the seismic loading, we are designing approximately 475-500 year return period loading for the seismic ultimate strength design. But that 475 is not, that 2/3 of MCE is not always 475. In Thai code, if you convert that MCE to 2/3 of MCE, it will be approximately 1,000 year return period. It depends on the location. But in the new ASCE 710, ASCE 716, the wind load parameters are changed. In ASCE 710 and 716, wind speed showing in those guidelines are already 700 year return period. So if you use those codes, you do not need to multiply with 1.6 load factor in your load combination. First you have to check your wind speed is 50 year or 700 year. If it is 700 year, do not need to multiply with 1.6 in the load combination. If it is 50 year, you still need to multiply. But seismic return period is still the same. So I will stop here for today, and I will continue for the design part and other definitions in the next lecture. So do you have any question about current one?
For the crack section in the beam for the crack that you will happen. I want to know what does mean crack section? It means under the neutral acid, you don't consider the concrete, right?
Yes, correct.
Same in the RC design criteria, right?
Yeah.
Okay.
For example, when you do the ultimate strength design for the beam, you have the concrete stress block at the top. And from that concrete stress block, after that, you do not consider the concrete, and you consider for the tension side, you consider only steel in your design. Okay. So when you calculate for example, you can calculate the moment of inertia of that concrete section, considering both concrete and steel, 100% concrete and steel. You can calculate by the moment of inertia of concrete BH2 by 12, and also you add the moment of inertia considering the rebar, and you combine that with moment of inertia. Okay, you will get that one will be the gross section, not the crack. And also you can calculate the moment of inertia of the concrete section considering only the top and the steel, using the transform stack section, using the modular ratios. Then you can compare that two ratio. It will be approximately 0.35. So that's the value coming from that. But those stiffness modifiers varies on the engineer designer's judgment. For example, we also considered cracking
of the structural members under the wind design, under the wind ultimate strength design, if the wind intensity is large. Not only the seismic. Even the seismic, if we contact the performance-based design, we have different sets of stiffness modifier for very strong earthquake, and also for the frequent earthquake, we have different sets of stiffness modifier. So these things can vary depending on the project, and also seismic intensity, and also wind depth. But generally, we have to use the crack section according to the code when you contact for the seismic design. Now we are designing seismic loading just 2/3 of MCE and design for that. And we assume that after we design that level of earthquake only 2/3, and if strong earthquake MCE level 2500 year return period camp, what will happen? We assume that if we design for that 2/3, the building will not collapse when the maximum considered earthquake comes. This is our assumption in the when we contact the code-based design. And also we assume that if the frequent earthquake comes, very small intensity earthquake which can come 50 years during the lifetime of the building will be operational. It means that no major damage. The building remain elastic, and we can occupy the building just after the earthquake without major repair. So we assume that if we design for 2/3 of MCE, the building will be serviceable under frequent, but we did not check explicitly. Just design only one level of earthquake. But we assume extreme earthquake, if extreme earthquake comes, it is not collapse. But and also service level, if frequent earthquake comes, the building will be serviceable. Okay. But in performance based, I think coming lectures we may present some introduction to performance-based design. In that case, we check for both levels of earthquake. For very strong earthquake, MCE level explicitly, and model nonlinearity, and check everything to prevent collapse. And also check service level earthquake, frequent earthquake, to using response spectrum analysis to design the building remain lasting. Okay. But here, code-based design, we just design only. So that's all for me, and I will explain to you the design portion.
Không miễn tẩu rồi. Bên đó. Đi à rồi lên khô được thẳng.คือรู้มันดีขึ้นเลยเพ่งก่อนเพ่งก่อนแล้วเคาะนะโดนแล้วพี่อย่าทาย